Hey everyone, welcome to the first video for section 3.2. So in section 3.2, we're going back into more of the theoretical type stuff that we saw in 2.4 and 2.8. And again, we're not going to really prove any of this stuff, because it's well beyond the scope of this course, what we would need to use in order to prove these things. But we're still going to talk about them because they are useful. They are things you should know because they help you to determine that, if I do a couple certain things, then I automatically get all the solutions I want. Any solution to this system, or to this ODE, is going to be of this form. So that's really the main point of these theorems, is the uniqueness statement, where once I get a solution, I know it's the only one, and there's nothing else crazy going on. So we're going to state a couple of theorems, do a little bit of the proofs for something that is not too bad, and then basically just go through the section and move on. So let's go ahead and jump on into that. So section 3.2 is more of the theoretical stuff like I just mentioned before. So we're starting with a second order linear ODE. Y double prime plus P of t y prime plus Q of t y equals G of t. So now for some of the stuff that we're going to do in this section, in this video, some notation is going to be helpful. So we're going to define an operator L for linear, that's going to let us write this in a nicer form. So we define an operator, I'm not going to say more about what that word means, L, so that for any phi, function phi of t, L applied to phi is another function of t. And what this gives me is phi double prime of t plus P of t phi prime of t plus Q of t phi of t. So for any function phi, I can throw it at L, and that spits out another function. That's why it's called an operator, because it sends a function to a function. And it has this form, it gives me this expression, which means I can rewrite the ODE as simply L applied to Y equals G. So I can drop the of t's because they're both sides are of t, but if you want to write that in, you can as well. So that's a problem we're trying to solve. And we also want to see if we added initial conditions, do we get existence and uniqueness, right? Because for first order equations, you could solve the problem, and then once you threw the initial condition, you could talk about if the solution existed or if it was unique. So along with initial conditions of this form, which, as I mentioned in the last videos, we need two initial conditions to specify a problem, and we'll see why in a second. We want to know if we have a solution and if it's unique. And thankfully, we have a theorem in the book. This is theorem 3.2.1, which tells us exactly that. So I'm going to write that up, and then we'll talk about it. All right, so here is that theorem. So if we look at the initial value problem, y double prime plus p of t y prime plus q of t y equals g of t, with two initial conditions, as long as we have all three of our functions, p, q, and g, are continuous on an interval alpha to beta, with t naught in that interval, this should look familiar because this is a very similar condition to what we had for our first order linear equations, where we had as long as our functions p and g were continuous with our initial value somewhere in there, then there exists, or there is, exactly one solution. So there's our existence and uniqueness statement, phi to the above problem, and phi exists all from alpha to beta. So this was, again, the linear condition, the linear result we had before, where if we had everything continuous on some interval, our solution existed up through that whole interval. This was different from the nonlinear case where we know it existed somewhere, but it might not exist all the way up to the boundaries of continuity. So the result here is very similar to that we had for first order equations, except now we have three functions to be continuous instead of just two, and we need two initial conditions. Now, this theorem is very hard to prove. Existence is not bad sometimes, other times it's awful, but we're just going to take this as fact and move on because there's no point spending more time on this. It just is what it is, and we're just going to take it as fact and move on. The things you'll be able to do with this are the uniqueness statement, that there's exactly one solution and only one solution, and the whole interval of existence stuff like we had before, whereas if P is discontinuous at a point, our solution isn't going to exist past that point. So let me do a quick example of how this works, or for the uniqueness part, and then we'll go on to some other stuff for this video. So here's the quick example of this. If I look at this equation, I want to say find all solutions to y double prime plus p of t y prime plus q of t y equals 0, y of 1 equals 0, y prime of 1 equals 0. Now, if you look at this for a couple seconds, you might be able to find one solution. And one solution is fairly obvious, and that is just y of t is 0, always. It meets the initial conditions, and if I plug in 0, the whole left side just vanishes, so I get something that matches the equation. And now the result that we want is uniqueness says this is the only solution. So we're done. The only solution to that problem is just the constant 0 solution. So if you ever see a problem like this, the answer is just 0. And that's it. There's no need to look for other solutions. It doesn't matter what p and q are. The only solution is going to be 0, as long as everything's continuous at 1. All right, so that's nice, being able to have this existing uniqueness sort of stuff. The other reason linear equations are great is because of the next thing, which is called the principle of superposition. And we will take a look at that right now. So superposition, I also wrote down the differentiation operator L because I'm going to use that again right here in a second. So what this says is that assume L of y1 equals 0. So y1 is some function, and L of y2 equals 0. Then for any constants, C1 and C2, L of C1 y1 plus C2 y2 equals 0. It doesn't matter what constants I pick, I still get 0 when I take linear combinations of my functions. And that's why we say things are linear, because they obey linear combinations and all that fun stuff. So let's look at the proof of this real quick, or at least a sketch of the proof. So what things show up in L? Well, phi shows up in L, phi prime shows up in L, and phi double prime shows up in L. So let's let phi equal C1y1 plus C2y2. So, well, what is phi prime? Well, phi prime is going to be C1y1 plus C2y2 prime. Well, derivatives are linear, so this is just C1y1 prime plus C2y2 prime. And the c's are constant, so this is just C1y1 prime plus C2y2 prime. We can do this again. What is phi double prime? Well, that's going to be C1y1 prime plus C2y2 prime prime. And if I do the exact same steps, what I'll see here is I get C1y1 double prime plus C2y2 double prime. And now I want to plug this into L. So write L of phi is phi double prime plus p of t phi prime plus q of t phi. So this is C1y1 double prime plus C2y2 double prime plus p of t times C1y1 prime plus C2y2 prime plus q of t times C1y1 plus C2y2. And now what I want to do is group all of the y1s together and all of the y2s together. So I'm going to see a C1y1 double prime plus a p of t C1y1 prime plus a q of t C1y1 plus a C2y2 double prime plus a p of t C2y2 prime plus a q of t C2y2. And now I want to factor out the constants from the first part and the second part. So I see a C1 times y1 double prime plus p of t y1 prime plus q of t y1 plus a C2 y2 double prime plus a p of t y2 prime plus a q of t y2. But now what is this? This is just L applied to y1, and this is just L applied to y2. So I get C1L of y1 plus C2L of y2, but we assumed this was 0 and this was 0, so the whole thing is going to be 0. So what did we just show here? Well, we just showed that if y1 and y2 solve y double prime plus p of t y prime plus q of t y equals 0, then so does c1y1 plus c2y2. So the idea is that from two solutions here, I get an infinite family of solutions with two parameters because this C1 and C2 can be any constant. So if I'm just getting any two solutions, I get an infinite family with two parameters for my solutions. And the hope is that with two parameters, I can pick my initial conditions for my function and its derivative independently of each other, so I can get any set of initial conditions from just this family of solutions. Now, the result of that is what we're talking about in the next video, where we show that in the right situation, we actually do get enough, that this linear combinations here are enough to give us every solution to the ODE we want. All right, so for this video, I've got one problem for you to look at. We're basically seeing that this idea of superposition and multiplying by constants doesn't work for nonlinear equations. So I'll give you an example to look at where an equation is satisfied by a certain function, but a multiple of it does not satisfy the equation. So you're going to check that for your problem for this video. So I'll put that up for you right now. All right, so here's your problem to look at for this video. It's a first order ODE, so back to first order because it's the example I came up with. But you're showing that one function is a solution, but the multiple of it is not, which does not happen for linear equations because you can multiply things by anything and still get solutions. So take a look at that and put that on your worksheet. For the next video, we'll start talking about how we know that just from this family of solutions, we can get every solution we could ever want. All right, thanks a lot for watching, and I'll see you in the next one.